On problem 5, we have a situation where water is flowing in a tube, and the tube maybe gets narrower. Actually, I don't think the situation was specified on this problem. We simply said that the velocity at one point is greater than the velocity at another point. Now, if you have a velocity v1 here and a velocity v2 here, and if the height remains constant, so that the fluid has these velocities at the same height, but at different points, then p plus 1/2 rho v squared is constant, and it follows that p1 plus 1/2 rho v1 squared equals p2 plus 1/2 rho v2 squared, where 1, the subscript 1, refers to one point in the fluid, and the subscript 2 to another point. So let's say that point 1 is over here, point 2 is over here. So that v1 is the velocity at point 1, v2 is the velocity at point 2, p1 the pressure at point 1, p2 the pressure at point 2. Now, if we rearrange this equation, we see that p2 minus p1, which is the change in pressure from one point to another, has to equal 1/2 rho v1 squared minus 1/2 rho v2 squared. That's a simple algebraic rearrangement. We just subtract p1 from both sides. We'd have p2 minus p1 over here. Then we subtract 1/2 rho v2 squared from both sides, and that would appear over here. Then we switch the sides. So the algebra is pretty straightforward. The change in pressure is therefore the negative of the change in 1/2 rho v squared. We say the negative of the change because the change in pressure is the second pressure minus the first. The change in 1/2 rho v squared would be the second 1/2 rho v squared minus the first, but what we got here is the first minus the second, which is the negative of the second minus the first. So the change in pressure is this. So if we know the two velocities, then we can calculate the change in pressure. If we happen to know the initial pressure, of course, then we could find the final pressure. But at least knowing the two velocities and the density of the fluid, we can find how much the pressure changes.